Okay. Sorry, guys. This isn't working.
Yeah. I think you only got it anyway. Yeah. That's true. So you guys show up. Yeah, you're on.
Yeah, you were. Why don't I have your thing? Anyways, okay. All right, let's cover this stuff, guys. All right. I hope everyone's doing good. Welcome back to fall or spring or whatever's going on outside. Today we're gonna be talking about a really important concept. I know I say that every week because it is really important. But this is the baseline of where we get all our stuff: geotechnical engineering, all the design, all the analysis, all the soil classification. We do this on soil samples that we have to retrieve from the ground and underground. Remember when we're doing these tests, it's going to be dependent on the geology. It's going to be depending on how many structures there are, the type of structure, but all of it starts with the subsurface exploration. So what we're going to be introducing today is just wide cast net about just general subsurface investigation. And then on Thursday, we're going to be focusing in on the two most common, most widely used types of subsurface investigation: the standard penetration test and the cone penetration test. So where we are in the schedule, this is like the one class I'm teaching that's actually on schedule. So thank you guys for helping me with that. So just giving you a heads up, the next few weeks are going to be a little sketch, as they say. So actually next week will be okay, right? Week 8 we'll be here in person. And then March 4th, we'll have a video lecture on March 4th, and then no class on the 6th. And then 2 video lectures after that, and then spring break, and then boom, exam. So it, like, you guys know yourselves, your study habits, your work ethic, like, be proactive in these next few weeks, because there's going to be less accountability of me in person here during this time, so just keep that in mind. We have these next few weeks of lab, which is nice and consistent. So your lab reports should be due this Friday. You should be an assignment for that, or grain size distribution. Please, please, please just double check and make sure it's in log scale when you start doing that. Every year, there's still a group that submits it where the x-axis is not in log scale. So I'd love to have finally a year where there's none of that, like, simple mistake. So for the sieve analysis, make sure that's the case. Other things this week, our lab number 4, the hydrometer, is this week. So that's, you'll be working with Joseph in that. Your homework number 2 has been posted. Half of it is based off of soil classification, and then the other half is what we're covering this week. But I made it due March 2nd, so you guys should have plenty of time for that. And then a normal week, which means we have a quiz, and that'll be due this Friday. So just putting that on your radar. What's up?
Lab homework is due Friday, 2024.
Yeah. Okay, I'll change that. All right, this Friday? That's the lab. Which homework is?
Lab B.
Okay, thank you. I will change that. Yeah, it'll be this Friday is when everything is due. Yeah. Thanks for letting me know. Okay, the only other thing I want to pitch here is this Thursday we have our Beers with Engineers. It's E-Week. Happy E-Week, everybody. It's like right up there with Christmas. I don't know really what it is, but it's fun. It's like the one time of the year where when you work at a company, you guys will get like barbecue and days off and all this fun stuff. But this event is at Wicked Barley. It benefits ASCE, the student group, which I know a lot of you guys are already included with. And Wicked Barley, I mean, let's be honest, it's one of the best breweries in here simply because of the kimchi fries. I'm going to be killing some kimchi fries right there. So yeah, this Thursday, I know there's not much of a deadline, but talk to anybody in ASCE and they'll give you more info on that. Okay, subsurface investigation. So chapter 6 of this textbook, which is, and chapter 12 of our Holtz and Kovacs book, And also when we start getting into the ASC or the ASTMs, I'll post those as well because there's ASTMs associated with most of these. Okay, so subsurface investigation. So obviously as civil engineers, we design stuff like this, right? Nice little house, stuff that goes on top of the ground. But us as geotechnical engineers, we have to worry about what's underneath it and how the things that we build on top are going to react to the ground or vice versa. So obviously we know any structure, any foundation, it's built on something, which is the earth. And so we have to have some idea of the soil below. Now we talked about geologic maps. Geologic maps are helpful because this can give us an generalized anticipated geology. Like here in Florida, I can just tell you, if we drill right here, we'll probably hit sand for the most part. We'll hit some clay or a marl layer, and then we'll hit varying layers of limestone. So I know the general geology of what's under here just because of working in Florida. But a lot of times we need to know the specifics. At what depth will we hit groundwater? At what depths will we hit that clay layer? At what depths will we hit that limestone layer? And what are the strengths and the weaknesses of those layers? So that's why every single project will require some type of subsurface investigation where we come out with a drill rig of some type or some type of way of testing underground. And we actually drill or probe or push something into the ground to measure the different layers underneath it. So instead of guessing, oh, we should hit a sand layer between 0 and 30 feet, we can actually ground truth and verify, okay, this sand layer turns to clay at a depth of 55 feet or whatever. Now, this is also really important because this will help us identify anomalies. We've already talked about those in some case, and we'll talk a little bit more about these, like internal erosion or karst conditions or holes in the limestone where we might have voids. So this is really important for also identifying hazards or other types of design limitations. And this is also how we get our soil samples to the surface, and we can classify them in the lab and do these lab experiments that we're doing on. So although like we've been giving you guys in the lab a bunch of like jars of dry sample or whatever, think of it, normally these lab experiments are taken from samples underground at various depths. So we're going to talk about those methods and procedures to collect those soil samples. Oh, I've already shared some of these, but obviously we can all probably visualize some cases where these subsurface investigations, if we don't do them thoroughly enough, that we could miss one. And even though this could compromise one aspect of our structure or one foundation, obviously there's cases where that could compromise the entire thing, like in the St. Leo Bridge here, where one pier settled and it put the whole structure out of service. And then of course in Florida too, we have sinkholes. We've shown pictures of these before, where if we build our drainage area on top of a soil condition that might be prone to internal erosion, then we might be expediting the internal erosion and the sinkholes later on. Another good, interesting comment, or another interesting case. What is this? Come on. Sorry. Okay. Another comment of this poor site investigation. This is, can't really blame it, happened a long time ago, but if you're familiar with the Tampa area, these gypsum stacks, which is phosphogypsum, it's a result of the phosphate mining. They just stack these 200-foot tall stacks on top of a soil group that is very vulnerable to sinkhole formation. So when we're planning and constructing some of these new gypsum stacks, some of these new landfills, they're spending a lot more money now to ensure that they're not putting it on top of ground that is vulnerable. And in 1994, 2013, and 2014, I think it happened again too. But some of these sinkholes have opened up in underground. Obviously, the sinkhole started like hundreds of feet underground, but it propagated up to the surface. And all of this groundwater that is wastewater is now pouring into the aquifer, which a lot of people in Tampa and Orlando and Polk County drink. So obviously you have these really important scenarios where we have to get rid of this waste, but we need to get rid of it effectively. So we need to ensure that the site that we're putting it on is safe. Not only do we care about like anomalies, but also we need to ensure that we are measuring the right values. So like when we start talking about design of different types of structural foundations, and if you take advanced design of structural analysis, advanced foundation design with me next semester, then we'll talk a little bit more about this. But we need to ensure that we're using the right tool for the job to get the information we need to design effectively. Geotechnical engineering is a little bit different than structural and concrete, or where the materials are a little bit more defined. Like we're going to test the yield stress of concrete or the compressive strength of concrete or the tensile strength. And all the formulas and all the design equations are kind of based off of that one variable. Geotechnical engineering, the designs are all based off of the specific type of structure we're constructing. So for a retaining wall, we would have certain variables that we need to design against, or certain soil parameters that we need to determine. So if we don't do a correct site investigation, we get issues like this. This occurred outside of Istanbul, Turkey. So this is a massive excavation. We don't have many of these excavations in Florida, but this is a slurry wall that has back and then these bracings up here. Projects we're working with really large potential like catastrophic yeah. Well, if anyone speaks to yeah, everyone got out, but I'm sure the people who own that house up there are not happy, you know. So like this could have been construction issue, it could have been a design issue, but like as geotechnical engineers, the first thing that comes if this disaster happens is those are supposed to be the initial subsurface investigation report, because that's where this all starts. Like, did we have a good understanding of the site conditions? Like, is this soil pushing on the wall more than we would have thought it would have? And did we design that wall correctly to account for that? Did this structure on top play a role into it at all? So this would, anytime you have like a failure per se, it's always going to go to that first subsurface investigation report, which is why it's important to understand these things. I talked about this at the beginning of the semester too, but this is a good example as well of kind of like a man-made sinkhole induced where drilling for a salt mine over in New Orleans. This was that one video I showed of the lake sucking in all those giant tall cypress trees. Essentially what they did was they were doing the site investigation and the original planning for this new drill or borehole or something for the mine, and they were offset it too much, and it penetrated this salt dome or this cavity that's depth in feet, 3,500 feet below ground. And so what happened was all of that soil just fell into that cavity and created that massive sinkhole. So we're talking about very, very devastating, like ground collapses and movements here. And this could have been caused by, or this could have been like, this could have been avoided by just a proper subsurface investigation, knowing where that top of the cavity is, even though it is 3,500 feet below ground. If you know, okay, beneath me at 3,500 feet, there's this cavity, we're not going to drill in this area, then they'd be able to avoid that. One of the other common ones too, that's a site investigation failure or just not good enough understanding, is the Leaning Tower of Pisa. And there's a lot of geotech reports out there actually that shows it, where if you just did one borehole at the site, you would see certain conditions, and that is variable across the site. So it's actually a bearing failure because this upper clay layer is thicker in underneath one footing than it is on the other one. So of course, can't really get mad at them because this was 1,000, 1,500 years ago. They didn't have technology, but we want to avoid this type of failure now today. So the overall objective of a site investigation, and I'm using the word site investigation now because this is kind of falls within like this term called due diligence in development, where part of the due diligence stage is understanding just generally what are some of the constraints or what are some of the benefits or what are some of like the limitations of the site that you want to develop. So it could be underground, it could be nearby, it could be above air restrictions, all these things. So the purpose of a site investigation is first, obviously, to determine if it is suitable. So what is the type of structure that you're planning? Is it even is a type of structure even an option for the site? So can we even construct it here? Is there a swamp like right next door where we can't put a landfill? Is there a air clearance where like we can't put a high rise because there's a nearby airport and you can't have the planes coming in? Or is it actually like just a limitation of the soil? Like this type of loading that we want to put here is not applicable for our site because it's a swamp or it's clay and it's highly compressible organics or something. So what we look for is also the geomaterials available. So this would be like, is your site filled with that A3 soil or SW or some of that good stuff that we talked about? And there's certain design parameters that we want to look for. Obviously, I've kind of used these before. Actually, I'm not going to say that. So I want to say, is it safe? Against bearing failure. So safe against bearing failure. Is it safe against compression? And then, of course, the cost of it too. So we'll talk about what bearing failure is and compression is at first, but just think of like settlement is compression, right? Like if the whole structure is going to settle because the soil is compressed, or is the structure going to tip over or fail because of bearing failure? And that's shear failure. That's when the soil actually like slides out, like in a landslide or a slope failure. And of course, the cost too. Like, is this something that is even applicable for us? And basically, what we want to do is, from a geotech standpoint, is consider the type of foundation that is going to make the most sense for our proposed structure, whatever that is. So is it going to be a shallow foundation or a deep foundation? So piles versus like a raft foundation or like a mat foundation. All of those come with their own constraints. All of those come with like a different cost, different contractor, all that kind of thing. Yeah.
So if you're working on a project, and I think it was mentioned in like one of the beginning slides, like how limestone can change from like limestone to like silty limestone over time. If you're building, like if you place a building on it and it shifts because of that sediment change over time, who is responsible for that? Is it still you guys for not like taking that into account, or is it just like who would be responsible for that?
Yeah, that's a good question. I don't know who would be the responsible party for that. There's this thing in insurance, not to get too far in the weeds, but you've probably heard of this whole like act of God thing that in insurance, where like hurricanes, sinkholes, natural disasters that cannot be proven to be predicted don't fall under. Like it's just like a, hey, oops, this is just kind of what it is. I don't know if that would cause in that because you can't really account for the degradation over time. But yeah, that's a good question.
It does take like a long time.
Yeah.
So
Yeah, most of the time it would be a compression issue for like a sinkhole formation or something, which then it could be, if you get a geotech report and they don't have that clause of a potential geotech or a potential sinkhole area, then it could fall on them. That's why a lot of reports, if there's a sinkhole that had been formed within this structure in the last whatever 50 years, then they'll include that in their site investigation report just to kind of like CYA, like just kind of cover their butt on it. But yeah, that's a good question. I don't know about the lime silt thing. So the other thing that we need to follow through with and really get an understanding is how will this construction change or potentially affect the nearby structures or property? And this is a huge thing that geotechnical engineers have to worry about, as you saw with that excavation. Oftentimes, if we're doing an excavation, it is going to be in a heavily developed area because we have limitations of space. So a lot of times, like if you're excavating soil or if you're tunneling to create a new subway system or something, the nearby historic structures need to be protected and they need to be monitored. And this is a big thing in geotech, where, as soon as construction goes on nearby, then all these cracks in nearby structures just magically start coming to the surface, and then all these insurance and lawsuits come out. So really that's something in the forefront that they need to monitor and really put in their site investigation, is if we do decide to move on with this project, how could it potentially affect some of the nearby structures? Overall, engineers and geotechs in general too, they need to manage the risk, and that's often what we're doing. We're just managing the risk involved. So every project is going to have some amount of risk, and risk can be calculated or determined by a hazard, the potential of this hazard happening, and then the consequence that hazard occurs. So the risk associated with that. That's why a lot of times in geotechnical engineering, you'll have different design solutions associated with the level of risk that the client is willing to take on, or the level of liability that the client is willing to take on. So we have to think obviously wide in this case too, with multiple options. So some different aspects of a site investigation, or sometimes called due diligence in some disciplines. Obviously, we want to know the structural information. So what are the loads being applied at our site? The geologic conditions, so the geologic maps, the history of the area, the topography, hydrogeology, the general or primary soil layers, and then some of the anticipated engineering behavior and the depth of the bedrock. Now, all of this right here, the hydrogeology, primary soil layers, depth bedrock, this is when we start getting into some of the site-specific parameters, where we need to go from less regional and more local scale. So instead of knowing, okay, northeast, north of downtown Springfield area has these layers, we need to start really getting and quantifying where these layers are or what these issues are. And this is where that subsurface investigation comes into play. So these are all parts of that subsurface investigation. So think of it this way, there's a site investigation or due diligence, and then oftentimes you would include this subsurface investigation, or some geotechs will call it a soil exploration report. Yeah, but this is where we're actually going to the site before any development occurs, and we go and we test the soil, we do different types of tests, bring the samples to the lab, and we get an understanding of what to expect there. So maybe you guys have seen these trucks around before. Has anyone seen these on the side of the road? Yeah, definitely, yeah. Yeah, this is a standard drill rig, that most common types, but there's also track mounted rigs, and then swamp rigs and all sorts of stuff, boat mounted, all these types of rigs. So these are drill rigs. The same thing that, the whole purpose of this is to drill into the ground. And part of that drilling is then to collect samples. And we'll talk about the different sampling techniques. But at the end of the day, what we want to do is get some ground truthing and say, okay, where is the clay layer? Where is the organic layer? Instead of generalizing, knowing where it is, in terms of elevation at this point, where do these layers exist? And can we collect soil samples to bring back to the lab? Now, the issue is, of course, is that this drill rig is just giving us a whatever 3-inch diameter example of the site, right? So we're developing massive acreage, but only off of this much, like a little pinpoint on the ground. So this is where the subsurface investigation, the geotech you choose or you work for, really like earns their money, because they can save you a lot of money by knowing a lot about the site, or can waste a lot of money by over testing. So there's no like standard, or there's no like rule for amount of boreholes per project or per acres. Every geotech kind of has their own like goal or what they want or plan. But just to like put into perspective for cost, to mobilize one of these trucks out here with a drill crew and to drill like a, I don't know, like a day's worth of 60-foot borings, like 60 foot in depth, so not even that much. That mobilization usually is around like $10,000. So like that times whatever, like, you know, months of testing, it can get really expensive really quickly. So obviously you don't want to go out and bore every 10 feet, even though that would be nice, because then you would get a lot of information about your site. That would cost a lot of money. So we want to find this neutral area here. This is something that FGOT's handbook suggests, but there's no like actual standard. It's all just suggestions. So if you have multi-story building, we want to have a boring every 30 to 100 feet. And obviously that's really, really big. And then different things here, depending on the level of risk that you want. So an interesting example of this here is outside of Orlando on the northwest side near Ocala. Wekiva Parkway. Is anyone familiar with that region at all? Cool, sweet, yeah. Nice brand new highway that went out there in 2011. It looked like this. One of the things about this area, there's Apopka, or what's it called? Rock Springs and Wekiva Springs. There's a bunch of like natural springs in this area. Which means there is a lot of reported sinkholes. So all those little yellow dots are sinkholes there. And you can see there's Wekiva Springs or Rock Springs down there in the bottom right. So this is what the site looked like in 2011. All of these little circular lakes, this is a good evidence of previous sinkhole activity. Like this could have been like geologic years ago, you know, super long ago. But this is a sign that there's karst terrain in this area. This is 2011. In 2015, they put this $14 million highway right through here. So DOT is spending a lot of taxpayer money just for this highway to connect the outer loop of Orlando. And just for reference, in this one little 1.5 or 1.2 mile region of roadway, there was over 25 standard penetration tests, 94 cone penetration tests performed just in here, just because of the risk of sinkhole activity. So a lot of money is spent and concentrated in this area, where maybe this section here, which has a different topography, might not have as many frequent testing because they are more confident of this subsurface condition than that subsurface condition. So you can see that's only 4 miles apart on the road. So we're talking about very specific, like site-specific, localized conditions.
Even with all those tests, can the sinkhole still happen?
Yeah.
So it's really just covering your butt.
Yeah. So some of the other things that they did in this area, a sinkhole could still happen, but they're trying to determine whether is it worth building the highway, and they have all their risk metrics and everything. But one of the things that they actually did in this area was there's an embankment that they just turned into a bridge. So the bridge goes over seemingly nothing, but there's a high potential of sinkhole activity in that spot. So if you're driving over there, you wouldn't even notice it, but you're like, why is there a bridge that just is over grass? But there's a high level of sinkhole activity under there. So they're like, instead of putting a road in there, we'll just span it with a bridge and hope that it doesn't collapse in. So just, I mean, as an example, the previous table, 1 boring per 50 foot. Obviously, we didn't do that in this little small example of it. So all that to say, this is the general flow chart of subsurface soil investigation. So we first have that soil geotechnical engineering problem. our preliminary site investigation, which tells us where the wetlands are, where the potential soil types are. And then this is where you would kind of do this due diligence side, the documentary evidence, field reconnaissance, local experience, like talking, like there's a lot of stuff that can be learned about a site just by talking to the farmers who used to like work there, or the landowners who've been there for, their families have been there for hundreds of years. You know, Google Maps only goes so far, documentation only goes so far. Then we get into the main site investigation, which includes these, and this is where the geotechs really come into play: drilling and sampling, laboratory testing, and in situ testing. And oftentimes what we do is a iterative technique. So we'll first have our first round of initial subsurface investigation and drilling. And then if we see an area that is a little bit like sketchy or a little problematic, then we would go back and do a phase 2 study just to hone in on that one specific condition. And this helps the project kind of be a little bit more streamlined. So let's say you're doing a multi-phase like residential area, you would do a blanket geotech report for it, and then be like, well, okay, this northwest corner has some potential problematic soils, but the other quadrants are okay. So you can start constructing on here, but we suggest doing a little bit more in-depth like design and analysis over on that northwest corner, you know? So that allows, this iterative allows the client to still have progress in the project without like slowing everything to a stop. So some of the very baseline, well, what I should say is what we're going to talk about today mainly is are these, and then we'll talk about the in situ testing too before, where the different types of probes and sensing and monitoring that we can do. So one of the most common types is a test pit. That's exactly what it sounds like. It's very easy to go out with an excavator, like you see on this top left, and just like do one little streak of the excavator to see what type of soil there is. This is really helpful when we're talking about like looking for potential borrow pits, like where is the soil on our site that we can use for fill dirt? You know, if we need to build an embankment, you know, 100 feet that way, can we use this here? The picture on the right is more of like a nice looking archaeological, or whatever that word is, where they do all these nice little cuts. Most of the time, the engineer would just come out with a backhoe and figure that out. Obviously, limitations are known here, right? There's shallow depths. You can't really go too deep. If it's really muddy, it might be hard to get a backhoe back there, or you don't want the excavator to get stuck. But it's really good for identifying organics. We used a lot of these. I wasn't working on this project, but when they were developing Seven Pines just south of us, right? The geotech contractor for that, they did a lot of these because during the pine, or the days of like when the Davises or the Skinners, whoever owned that, like had a lot of trees and stuff, what they would do is like they would, I forgot how they did it, like in order to strip like the bark off the trees, they would put them in these big vats and like pour chemicals or something, like to just strip the bark off of it to then take the wood out. And so like some of those ditches were then buried under, and obviously they want to find those ditches where they used to just fill in with organics and all the bark and stuff. So what they did was they would just go out and with the excavator, like do a scoop. It's like, nope, it's not here. Do another 100 feet, scoop, nope, not here. And then be able to delineate and find where some of these organics or some of these like tree filled ditches are. So really, really fast and really helpful for that. And again, you get the soil profile directly exposed. And also, if you plan it out right, the trench can be used for utilities. The disadvantages are obvious: limited with depth. And then it's also limited with the groundwater table. So if you have a very shallow groundwater table, or if you're in a swamp, you can't be digging a test pit. So I shared test pits because this is an option and it is used in Florida. We're kind of starting from most basic, and then we're going to be getting more sophisticated as we go on. So think of it that way. So really, for a test pit, you just need to know somebody with an excavator. It's not too hard. Everybody has a friend with an excavator, right? If you don't, it's a good friend to have. All right, the other one, which is something we've used, is the hand auger. This allows a little bit more precision of identifying the soil types, but of course it can be still limited to depth, 10 to 15 feet, depending on soil conditions. But it allows us to more meticulously retrieve some of the soil samples where an excavator might be mixing everything up, you know. So it's really good for initial site investigation, especially in an urban built-up environment, because we can tell if we are about to puncture like a gas line or a sewer line or electricity line, where an excavator might not have that finesse, you know, as you're digging through it. So the advantages of this, obviously super low costs like $20 to pay an intern to go out to a site in the middle of summer and do a hand auger. And it's also portable. So a lot of projects will start with this, especially for roadway projects, especially if they're looking to identify potential fill sites. Like if the area is known to have like good fill soil, then they'll send somebody out there with a hand auger to do like 15 feet grid spacing in a certain area to see like what the layers are where this good fill soil is, like the A3s and all that stuff that we talked about. You can read the disadvantages. You guys all know those things. All right, so now what we're getting into is a little bit more of the stereotypical drilling types. So in order for us to retrieve samples from deeper depths, we can't use a hand auger, we can't use an excavator. So in order to drill, this is one of the oldest and still existing, especially in some like developing areas, where you essentially use a pressure washer, a rotary washer. So this can be set up through like this derrick technique here. But the goal of this is to circulate water at a high pressure that essentially erodes the soil out so we can dig to a deeper depth. And so this is essentially like taking a garden hose and at a high pressure and just like digging a hole with a garden hose. It's very versatile. It can be a little bit of a pain to drill because this is the drilling, and then you would have to pull the whole drill rod out and then do the sampling underneath it. And also it's very heavily disturbed because you're washing everything out. So if you're trying to get like a natural moisture content of soil from a sample, this might not be a very good test to do because you're spraying it with water. But it's still used a lot, rotary wash method. And this is one of the methods that we would still use on the drill truck today. It's combined with a drill bit though. So it's not just pressure washer, but there's still this rotary and a washing of soil samples up. This is also really common. Let's say in Florida, you have to go back and retest the soil sample at like 200 foot in depth or something. Like let's say the client during this phase 2 is like, actually, we want to increase our structural loading. Can we get some more samples from 200 foot in depth? You would use the rotary wash method to get down to that depth and retrieve your soil sample, like because it's a much quicker test. You have a question?
Is that also called daylighting?
I don't know. I've never heard it called daylighting before. I've heard of daylight. When I think of daylighting, I think of like rivers and stuff that were buried, and now you are like restoring back to the natural thing. Like I know McCoy's Creek, they're daylighting. It used to be underground in Brooklyn neighborhood, and now so I don't know. Yeah.
So they're gonna use that to get down to it. What's the other thing that they're gonna use to get that?
To get the soil sample? Yeah. No spoilers, man. I'll get there in a little bit. But yeah, no, we'll talk about the sampling technique. We're still on the drilling side of things. Do you guys understand this? This hopefully, yeah, this makes sense. I won't go through all of these here. All right, now we're getting to the soil sampling. So once we get to the depth that we need, there's different ways of getting the soil samples back up to the surface. So in general, there's always going to be like a combination of both of these, where you have drilling and then sampling occurring. So you would drill to the depth, and then you would replace that with a sampling technique, and then you'd retrieve the sample and then drill and then sample, drill and sample. So that's why like the mobilization costs and the cost of this is pretty expensive. And that's why when it gets exponentially more expensive with depth, because if you think about it, like when we're drilling 200 feet below ground, we are putting 200 foot of rod into the ground and then pulling 200 foot of rod out of the ground, replacing the bit with a sampling bit, and then putting 200 feet back into the ground and then getting the sample. Yeah.
Oh, they just suck all that water out of the bowl instead of fill it up with water, they leave all the water in there because they don't get this out.
No, yeah, you leave all the water in there. Yeah, it's a slurry, a mud slurry, bentonite slurry, which keeps it open. Well, but there's a valve. You'll see pictures of it. But yeah, that's a good question. Okay, so but there's two general things we need to think about when it comes to sampling. There's the disturbed samples and then the undisturbed. The other way of like referring to undisturbed is high quality. Basically, we need to think of what like the soil, do we care about it being in its in situ fabric or state? Because the result of us moving it to the surface is going to change the stress state, change the fabric, the minerals, the crystallization, all that stuff. But what we care about is in its natural state whenever we are like loading it, right? Because we are loading soil in its natural state or stressing soil in its natural state. So we need to be considerate about this. Obviously, there's some types of lab testing that we can do on disturbed samples, such as like the grain size distribution. So lab 3 that we just did, right? Like this doesn't matter, like whether those are through this test, everything gets disturbed anyways. So what we care about mainly is like the sample, like, you know, the ratio of the thicknesses and stuff. A few other things like specific gravity. This is also something that can be performed on disturbed samples. Organic content. Soil classification. And then even the Atterberg limits, which we're going to be doing next week. But when we are talking about strength, like measuring strength directly, this is when we have to consider undisturbed samples. So some of these would be like something called the consolidation test, where we're looking at measuring the compressibility of clays. Or something called the triaxial test, which measures the shear strength of soil. Or the hydraulic conductivity, which are all fun, fancy words. This is the permeability or the ability for water to travel through the pore space. So all other strength tests, we usually care, or we usually need what we call in situ conditions, or like what is the soil like actually under the ground. So if we were to use a pressure washer to bring up the soil, we are remolding it, it's just in a completely different state. So we can't like test it in the lab and say that that testing condition is equivalent to what is actually underground. So the different sampling methods here. Do you need me to go back? So we've drilled our borehole at our site, and now we need to choose the different sampling method. These are the range of the different types of sampling methods, from auger cuttings all the way up to piston samplers. And this ranges from disturbed to high quality. And we'll talk about each one in a little bit. Auger cuttings, everyone know what an auger is? It's like a pipe with a screw on the outside. It's basically like a screw where you would twist it and it would move the soil cuttings up. But if you like were to ask like a kid to draw a drill, they'd probably draw a little squirrely thing or something. That's essentially what it is. So we still use auger cuttings. This is a nice way of doing it because for auger cuttings, you don't, it kind of does both the drilling method and the sampling method, because the auger is also drilling into the ground and bringing them up. But that soil that's at the surface is completely, disturbed. Split spoon sampling, which is one of the most common types. This is used for our standard penetration test, which we'll talk about a lot. Shelby tubes, which is called a thin wall sampler, piston sampler, and then obviously block samples, but that's limited to depth. Like that's where you actually excavate and trim out by hand. But at the end of this, what we want to do is bring soil to the lab to test it in the most natural state possible. So this is a split spoon sampler. So it is about 2 inches in diameter. It's open on one end and has a little sharp cutting blade here. So this would be at the end of the drill rod. And the whole thing is filled with what we call a bentonite slurry. So bentonite is like a type of clay that makes the water a lot more dense. So it actually holds the borehole up and it pushes the groundwater table away from it. And so we would drop this with the drill rod back through the hole. And there's a valve there at the bottom that will let the water release. And it's a spring-loaded valve. So whenever it's being filled with soil, it closes that valve, that little check valve there. And what this does is we will then hammer this into the ground at whatever depth our borehole is open to, and it will fill up with soil. And once it fills up with soil, we bring it all the way back up. So again, we bring the 200 feet of rod back up, and then we can unscrew it to retrieve the soil sample. This is an example of a Shelby tube. The Shelby tube looks very similar, but it's just a really thin pipe that has a sharper blade. And this is not hit, it is pushed into the ground. So we would use the hydraulic ram to push it into a soil sample. So this is Shelby tube. This is pushed, not hammered. A split spoon sampler is hammered into the ground, which when we go to the lab visit at CSI Geo later in the semester for lab 7 or whatever that is, they'll do a lab demonstration of what this looks like. This is essentially like pushing into the soil to fill up the tube, and then you remove it to then excavate it, or then to take the soil out. And this is a high quality sampling technique, or a undisturbed sampling technique.
So they drill the hole first, then put that.
Yep. Yeah. So you would drill down. This is used a lot for clay or fine grain soil. So you would drill into to a depth where you are starting to get to clay or something, and then you would pull everything up and then put this in, slide it all the way down to the bottom, and then push it through using the ram of the truck or whatever. So we have some of these in the lab that I can show you guys. We have some examples of these. So then what we do is we bring this to the lab and we'd extrude the sample out, and then we can trim it down and do our actual testing on the sample. And the goal is that we find a section of the sample that is undisturbed. So it was just hanging out underground, and then it just magically became to the surface. It wasn't hit, it wasn't hammered, it wasn't washed up. It's just like a very good representation of the actual soil conditions. The other types of things too, we have rock cores, and this allows us to bring samples of rocks up to the surface. This is really cool technology. Like it's called like I forgot the guideline or triple line or something. You can have a rock core where the outside or the whole thing moves, which causes a lot of friction, but now also you have double tubed where the outside drills down and then the inside will actually drill. and be able to get some of those really clear looking sections there. And then obviously the drill bit is important too. And this would have to have a good understanding of the geologic condition and the contractor there. Of course, in Florida, this is what our soil looks like. So we don't, like, yes, we do look to core rock material still, but you're not going to get that nice amount of stuff. But this is really important for macro porosity and that kind of thing. So the types of strength estimation. So these would be our in situ or our testing that we would perform while we're drilling to get an estimation of our strength. Is everything okay right there? So this is where geotechs love their 3-letter acronyms. We have SPT, CPT, DMT, PMT, VST. They really like the TLAs, the 3-letter acronyms. The most common one is the SPT, the standard penetration test. This uses that split spoon sampler to retrieve soil samples, but also measures the amount of energy the soil takes to move the split spoon sampler into the ground. And so we relate that to the strength of the soil. And that gives us an indication of where the weak layers are, where the strong layers are, so on and so forth. There's limitations with that, which we'll discuss. The cone penetration test is very similar, except there's no samples retrieved. It's just a cone that is about 1.5 inches in diameter that's pushed into the ground hydraulically. And that's all electronic. So we're not counting blows. We're not like sitting on the back of a drill truck. We're inside a nice air-conditioned truck that's measuring and electronically recording everything. So the standard penetration test, SPT, this is ASTM D1586. So the whole goal for the standard penetration test, this produces an N value. Let me start back. So we want to know the soil strength as a function of depth. And so what we do is this will give us an N value, which is in terms of blows per foot. And this uses the split barrel or split spoon sampler that we talked about before. So the way we get this N value is then correlated to different types of strength values. What we would do is we would first drill to a certain depth that we want to sample our soil at. And then we put the split spoon sampler on our drill rod, lower it back down. And then there is a 120-pound hammer that drill rods or drill trucks will have that then will fall 0.7 meters. What is that, 30 inches? I don't know. Maybe 30 inches. It'll fall and it'll hammer the drill rod or the sampler into the ground. And so what the engineer does on the back end of the drill truck will then count the number of blows it takes for that sampler to go 6 inches into the ground. So the hammer will swing over, you can hear it, it's like the ting, 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 and they will count the number of blows it takes to go 6 inches, and then another 6 inches, and then another 6 inches. So 18 inches total in first, second, and third increments. And then what we do to get this N value, since it's in blows per foot, we count the last 2 6-inch increments. And that is our N value of our soil. You do this way before pile driving, but yeah, it's correlated to pile driving, which is helpful. So remember, the N value is the summation of the second and the third increment. So why do you think we don't care, or why do you think we like still count the first 6 inches, but we don't count them in the N value? Why is that information just disregarded? Exactly. Yeah. Yeah. The drill, like, think of the whole process. There was a drill rod that was going down a drill bit, washing all the soil out. Like this first 6 inches, you know, there's going to be sediment that falls into the hole, like a bunch of stuff. This first 6 inches it might not be actually what the natural soil is. So we still write that down because it's important for the driller and the geotechs to actually know it. But the end value, we take out that first 6 inches and only care about those last foot, because this is what we're assuming is going to be a natural type of soil. So that's that end value, blows per foot. So this is part of the standard penetration test. And this is what, like if you've ever looked at geotech reports, this is what you'll see right there where we see N on there. So what we do is we do this with depth. One of the limitations is we can only find an N value every 2.5 foot in depth, simply because of how we calculate it, right? Where you can't like do a continuous N value because you have to wash the material out eventually. So we can only do every 2.5 feet. Most borings are going to be every 5 feet or every 10 feet. FDOT does require N values every 2.5 feet for bridge borings or like important structures. But that's what we see here with this N value. This is the depth. So this is the ground surface here. And then we have this with depth, and each one of those little tick marks is 1 foot. So you can see how the N value changes with depth. So we have pretty dense stuff, 20, 25, 35, and then some loose stuff. And then this right here where you see 50 over 3 inches, this means the driller got tired and didn't want to count above 50. And they're just like, all right, the hammer's been hit 50 times and it only has gone 3 inches into the soil.
It's 32 twos. It goes 15 to 2 and 15 to 2.
Yeah, so that's just a loose soil zone right before the limestone. So that might be a problematic thing. Like if they're putting a foundation in that area, they need to check. Because remember when this is the drill, this is a hammer hitting it into the ground. What they do then is like, let's say it only goes 3 inches. And this is like rough measurements. It's like a dude like with a chalk line and a stick, like measuring the drill rod in 100-degree heat. But let's say it only goes 3 inches, then they pull everything back out and then put the drill bit back on and then drill past it. And then once they get down and drill another 5 feet, they pull everything back up, put the split spoon sampler back on, and then put it all back in the hole and then ding, ding, ding. So it's a very long process, especially when you get really deep and into some of this weathered limestone and stuff. So with each split spoon sampler, they would then collect and put it in the boxes and then bring them to the lab, and then they'd give them to us to stratify, to do the grain size distribution, all the labs that we've been doing. So the advantages and disadvantages of a standard penetration test. The main advantage is it will obtain both a physical sample that we can touch, and a stiffness or a strength number, which is the N value. So although it's not the most sensitive N value because it's just a dude counting a hammer hit. Also, I should note too, like when the 6-inch increments, they just mark with chalk on the drill rod. So they have like a little 6-inch stick and just puts it on the drill rod and marks it. So it's not the most precise thing, but still like it gives us some relative information of the strength of our soil. It's many contractors out there, simple and rugged, hydraulics breaks down, but they can fix it. But there are some like clear disadvantages. Obviously it's very disturbed sampling. So the hammer, you're hammering soil, even though it's like a 2-inch thing, like, you're hammering the soil in there. And that's because it produces a very, sorry, this should say crude. A crude strength number or crude stiffness number, where like if we're hammering into clay or organics or some sensitive, smaller, like lower strength value, we might not get a clear understanding of the actual strength because you're just hitting clay with a hammer, basically. which means it's not always applicable to fine grained soil. So really understanding what the potential strengths are of our soil. Like if it's clay and it's very sensitive and very like quote unquote weak or soft clay, then doing this test, it's not sensitive enough to actually measure the strength or the stiffness. You're just hitting it with a hammer and you're saying, oh, there's zero strength. It's like, no, there's still strength there. Your equipment is just not sensitive enough to measure it. So some of the things, some of the tables that you might see, this N value is really, really helpful. So this is a strength value. This is called a friction angle, which we'll talk about a lot more later. It's a soil strength parameter. And then you can see the N values like correlated with this. So there's a lot of tables, there's a lot of steps out there that help us estimate the strength of it from the type of in situ test that we're working. Here's some more tables too for gravels and sands and silts and clays too. This is shear strength, which is another strength parameter. So of course, also though, it's a very rugged test. So you can do, anywhere you can get a truck, you can do these types of tests. I actually took these pictures when I lived on this barge when I was working for the Gandy Bridge that's now under construction there, where some of the other testing involves a little bit more sensitive electronics. You can't have exposure to salt water or be in the rain and that kind of thing too, like this next one that we'll talk about. So that's really beneficial here for the SBT. It's very, you can kind of drill wherever you want for it.
Would you guys have to like move that arch every time?
Yeah, every time we did a borehole, yeah. Yeah, these jack-up barges are really common because the tide is going to change a lot. So you need like a set datum. Obviously, we don't want our drill rising and falling. So, but we were doing like 200, 300 foot holes. So we would be on one spot for like multiple days.
How would you pull up your piles?
What piles? These?
That is supported on, yeah.
There's motors on each one of these. So they're just sitting on top of the seabed and they just pull up, like the motor kind of just sets the boat back down. Yeah, they're not like piled into the ground or anything.
You gotta get the tunnel there for you, or just
Nope, a little motor. Yeah, it was fun. I don't know, but I'm not a barge. I don't know anything about the barge. I think the dude spoke English who controlled it, but I didn't understand the English he spoke. All right, the other option about that we have, let me at least get through the cone penetration test overview here. So the other option, very common one, is a cone penetration test or CPT. This is another or ASTM, but this test involves a much smaller relative probe hydraulically pushed into the ground. So it's not hammered, it is pushed. This pointed probe is pushed and it measures the tip resistance against the probe. It also has a pressure transducer along the sleeve of it, so it can measure the sleeve friction. And it also has the ability to measure the pore water pressure. So there's a lot more instrumentation, a lot more like things that it's measuring compared to the standard penetration test, which is just measuring an N value. This also collects readings every 10 to 50 centimeters, which in our world is like 1 to 2 to 3 inches. So it's really good to get a strong understanding of the site conditions.
Would this be on, like, you can't use this in most places, right? Because most places are unshelled. So you couldn't get that back there.
Oh, you can put this on whatever you want still. But you can't, you can't push this. There's no drilling involved. This is all pushing. So let's say you hit like a really hard layer of rock. Like there's no way you're getting through that. Like this little drill rod, this sensitive like piece of equipment is not going to be able to push through rock. So you can only use this in areas that you know where the rock is and only the fine grained soil above it. But what it measures is the tip resistance, cone tip resistance, the sleeve friction, and then what they call this friction ratio, which is the ratio of the two. And the big benefit of this is it can be performed inside a truck where it has the push rod. This is like a little extender where the rod will be pushed through the center of the truck. So you use the truck as the reaction force. The weight of the truck is the reaction force. And so you have a computer that's reading out the results in real time, which is really helpful. And you have an air conditioning unit on this truck, which is very helpful as well in the summertime. But obviously a big limitation of this is it cannot be pushed through rock at all. So it's relatively fast. It does continuous profiling. So remember the strength values for a standard penetration test were every 2.5 to 5 feet. This is giving us strength values every 1 to 2 inch. So we have a lot of data, a continuous profile, and a lot less of a chance that we miss like some problematic soil. There's a strong theoretical basis for interpretation, especially when it comes to like pile driving and pushing. Essentially what you're doing with this is pushing a miniature pile into the ground. So there's a lot of like correlations to that. And it's much more suitable for soft clay soil because that hammer, you're just banging clay and it's just going everywhere. This is like a nice butter knife slicing through it and you can measure the resistance of it. The disadvantage is it's has a very high like capital cost or like overhead cost or whatever. You know, it's much more expensive to buy or to mobilize, but then you usually get a little bit more testing done because you can do like 5 boreholes in one day where you would normally only do 1 for this. Of course, the other major one is there's no physical samples retrieved. So usually they would always be combined with at least 1 standard penetration test nearby, just to make sure what you're pushing through is what you think you're pushing through. So you can correlate them for a site basis. And obviously, as we said, can't penetrate dense or hard layers. But we get a lot more data with that. All right, next class we'll finish off this and then we'll talk more into the specifics of standard penetration tests, some of the correlations, as well as the cone penetration test. See you Thursday.